Hello KCET 2026 aspirants. So welcome you all to Sankalp 2026 batch where we are committed to turn your dreams into reality, right? So today is the second class of this brand competitive new series. So now in the first class we have already discussed bridge course part 1 where I have covered physical and inorganic chemistry, all the basic things that you would be requiring for your class 12. Now in this video, that is your bridge course part 2, we will be talking more about organic chemistry. Okay, so I know many of you would have skipped your organic chemistry in class 11th, or you might not have been taught well in your schools. So you don't have to worry. Whatever basics things that is required for this particular organic chemistry of class 12 will be covered in this video. So here are some basic things. Okay, before moving forward, I want to tell you that why this series is going to be very important and life changing for you, because here I have some toppers of 2025 KCET who studied entirely from our channel. Okay, they were just from our YouTube they studied and they were able to get such great ranks. So we have Prajwal for 171 rank, we have 443 rank, we have Deeksha for 693, we have Samiksha 752, Sachin 934. Then we also have here so many other students from Harshit 1197. So there are so many ranks. So there is no doubt that you are on a reliable source. Okay, you can completely trust us for your KCET 2026 preparation. And now we want you people to be in the top 1000 rank in KCET 2026, and that is completely possible, doable if you work hard with us from today onwards. Okay, every day whatever we are teaching, there will, as we have discussed in the our launch session, that there will be every day 2 classes, 2 subjects. So just follow the same pattern and then you will be able to complete your syllabus on time, do revision, do question practice, and can be a top ranker, right? Okay, now so in this, what all things we'll be discussing is about carbon atom, first thing. Next we'll be talking about nomenclature, then we'll be talking about isomerism, and lastly about general organic chemistry. Okay, general organic chemistry means what are electrophile, nucleophile, what are the types of reactions, how do we show arrows and all. So those things I'll be discussing. Okay, next moving forward. Okay, before that, here I want to tell you certain things that you should keep ready with you before starting this class, or I can say rules to do this class. So first, sit with a notebook. Okay, just don't come and watch the lecture, because I'm going to discuss many important questions, also many important practice questions. So you have to sit with the notebook and at least 2 color pens you use. Okay, so that you can give proper heading and subheadings. Okay, and blue, black is fine, and if you add one red color or a pencil to draw arrows and all when we do mechanisms and all, so please take these things. Now if you are watching this video, please go back. If you haven't bring your notebook, please come with your notebook and at least 2 pens and 1 pencil. Okay, that's done, fine. Now we can move forward to the class that is all about carbon, the first topic here. Now in this, what all things we'll be talking about: representation. How do we represent the chemical or the organic compounds? What are the different ways of representation we will see? Molecular representation, condensed formula, bond line formula, expanded formula. Okay, these are the 4 things that I will be discussing under representation. Next we will talk about bond and hybridization. Hybridization I have already discussed in the inorganic chemistry as well, but here also whatever hybridization is required for your organic chemistry, that I will be talking. Types of bond and types of hybridization. Lastly we will talk about degree. What is your degree of carbon and degree of hydrogen, and how to find out. Also we will solve some questions with that. Okay, I hope the first topic of today's class, that is all about carbon. After the second topic is nomenclature, but I am hoping that the first topic all about carbon, what all things are there in this to study is clear to all of you. So let's move forward with the first topic, first subtopic, that is representation of organic compounds. Okay. So in representation, as I told you, we have 4 different ways. One is molecular formula, one is condensed formula, one is bond line, and one is expanded structure. Now before starting anything, one thing that you have to remember till the end of your life, I am telling you, till you are alive, one thing you should remember about carbon, that carbon has or carbon can form, so I want all of you to write it with big letters, carbon can form 4 bonds. Okay, till, please remember, this is the most important. If you know this thing, many reaction mechanisms, many formulas, many structures you can draw correctly. Okay, so one thing that I have to keep in mind today is that if I tell lesson of the day, the takeaway of the day you have to keep in mind is carbon can form 4 bonds. Okay, that is what you have to remember. Okay, now let's move forward with the all the types of the structure. Now very basic, I am not giving you any explanation here, you also don't have to write, you can just mention the example. First one is molecular formula. In molecular formula, what you have to do, simply you have to write the element, okay, how many carbons are there, how many hydrogens are there, how many oxygens are there. If you write together, that is called as molecular formula. Let me give you some example here. For example, I have C4H10. What does this molecular formula tells you? It tells you that in this compound there are 4 carbon and 10 hydrogens, right? Very simple. How many carbons are there? 4. How many hydrogens are there? 10. So if you just write the elements and below that you just write down the number of carbon and number of hydrogen is present, that is called as your molecular formula. And I hope this is very clear to all of you. Now moving next, suppose I write C6H12O6. Now this is also a molecular formula which represents what? There are 6 carbon, 12 hydrogen and 6 oxygen, right? So molecular formula, how to write, is it clear? Now we will take this as an example and try to solve all other 3 structures. Okay, so next one is condensed formula. Okay, so in condensed formula, what we have to do in condensed formula, remember, you have to show only carbon-carbon bonds. Okay, only carbon-carbon bonds has to be shown in the condensed formula. Now how many carbons are there? I am taking this as an example. Okay, so please remember this I am taking as an example. So there are 4 carbons. So let me do 4 carbons. Okay, now you have to adjust 10 hydrogens with this carbon. Okay, so how to do that? So now see, this one carbon is having how many bonds? Already it has formed 1 bond with this carbon, right? Remaining how many bonds it has to form? 3 bonds it has to form, because I told you carbon can form 4 bonds. Now 1 bond it has already formed with another carbon, right? Out of 4 bonds, 1 bond is already formed. Now 3 other bonds are left and that will be bond with hydrogen. So 3 other hydrogens are required. So I will write CH3. Okay, so you see you are not showing carbon hydrogen bonds here, you are only showing carbon carbon bonds here. Now moving to the next carbon. Now see, this carbon has already formed 2 bonds. Carbon can form 4 bonds. This second carbon has already formed 2 bonds. So out of 4, 2 I will subtract, 2 more bonds are left, right? So these 2 will be again hydrogen, right? Moving to the next carbon. Here also this carbon has formed 2 bonds. So 2 more carbons, 2 more hydrogens will be there. Now this carbon has formed only 1 bond and it will require 3 more bonds. So CH3. So remember, for the terminal carbons, the hydrogen should be written outside. Okay, for this carbon it is on the this side and for this carbon it is on that side. Right, this is what? This is your condensed formula. Now coming to bond line formula. Bond line formula is the easiest one. You only have to show, see, what you have to do? Only show carbon-carbon bonds don't write carbon. Okay, so here you see we are showing carbon-carbon bonds and we are writing carbon and hydrogen, right? CH is written. Here nothing will be written. 4 carbons are there, so just put 4 dots, 1, 2, 3, 4. These are 4 carbons and then join them. Okay, this is the bond line formula. Now you have to assume that this is 1 carbon, so it will have 3 hydrogens. It is 1 carbon, it has already 2 bonds, so it will have 2 hydrogens, it will have 2 hydrogens, it will have 3 hydrogens. So this is bond line formula. Okay, now lastly coming to the expanded structure. So in expanded structure, you have to expand this particular structure. You have to show all the bonds. Okay, so in expanded structure, what we have to do? We have to show all carbon-carbon and carbon-hydrogen bonds. Okay, so let's start. We have 4 carbons, 1, 2, 3, 4. And we have this first carbon has 3 hydrogen, so CH3. This is CH2, 2 hydrogens. This carbon has 2 hydrogens. This carbon has 3 hydrogen. This is your expanded structure, right? I hope all the structures are very clear to you. Now, which structures are mostly used? So generally we will use condensed formula, bond line formula mostly. Okay, expanded are rarely used, but yes, you should know how to represent it. Clear? Okay, moving forward now to do some practice questions. So only teaching will not help, right? We also need to do some question practice. So here I have, so first tell me these are which type of formula? These are which type of formula? These are your condensed formulas. Okay, so you have to write the bond line formula for each of them. Okay, bond line formula. Let's start with this. So first of all, when you are doing this structure, let's do the first one. Okay, see, you can see 2 CH3, you can first see this carbon. Okay, this carbon is having 1 hydrogen and 2 CH3 groups. Okay, then you have, when I write CH2 whole 2 means 2 CH2 groups will come consecutively. Then you have CH2 and then OH. So let's show that. So first I have this carbon. Okay, bond line formula, there will be no carbon required. Okay, but I am just expanding this one little bit so that you will be more clear. See, this one carbon has 2 CH3 groups, then it has 1 H group, then it has 2 CH2 groups in continuous. Okay, next I have CH2OH. Okay, this is, see, this is also condensed formula, this is also condensed formula. Here carbon-carbon bond is shown with lines, here it is not shown. Okay, that's the difference. Now we have to do it as a bond line formula. So for that, find the longest carbon chain. See, 1, 2, 3, 4, 5. I can have 5 carbons in one chain and this will be a branching. So I will do 5 dots. 1, 2, 3, 4 and 5. So 1, 2, 3, 4 and 5. Done. 5 carbons. Let's join them. Okay, done. Then you see on the first carbon you have OH group. So for OH group you have to show. For carbon and hydrogen there is no need to show anything, but for any other atom you have to show this one. Right, so this first carbon OH is there. First, second, third and fourth and fifth. On the fourth carbon you have a CH3 group. So just put a line like this. This also shows that there is a CH3 group attached here. Right. So this is the bond line for the first question. I'll draw it here, small one. Okay. I hope this is clear to all of you. Okay. Next, let's go to the next question. Question number 2. First, you can a little bit expand it. If you are not able to understand this formula, then you can convert it to bond line formula. Okay. See, let's go for second question. Wait. Yeah. You have CH3, CH2 whole 4, CHI, CH2, CHO. Now what does this mean? First I have CH3, okay. Then you have CH2 whole 4, means there are 4 CH2 groups. 1, 2, 3 and 4. Then after that I have CHI. So you have next CHI. Oh sorry, I is there, right? Okay, I is there, and after that again you have CH2, and then you have CHO. Now here you see CHO is like this. See, carbon should have 4 bonds, right? Already it is 1 bond with this carbon and 1 bond is with hydrogen, and oxygen form 2 bonds, so that is why 2 bond here. Okay, now let's show this one. 1 2 3 4 5 6 7 8 carbons are there, right? So 1 2 3 4 5 6 7 8. Okay, now if I draw this one, okay, and on the last carbon I have O and hydrogen, so this I will draw like this. Okay, to show that this carbon is having oxygen and hydrogen, or you don't have to even show hydrogen. Hydrogen is also not required. You can only show like this, or you can even write hydrogen. Now what I have, now see, 1 2 3, right? 1 2 3, on this I have iodine, so you have to mention here I. Okay, 1 2 3 4 5 6 7 8. That is the structure of the second question. Let's draw this one. 1 2, yes, is there. I am putting this H, okay, generally it is written. Then 1 2 3, here I will put I. Okay, now let's move to the next one. Yes, let's move to the third question, and fourth one I will give you homework. All of you should try it. Okay. Okay, I hope the session is going well and you are enjoying, students, right? All of you are enjoying. Any doubt, please put down in the comment section. I'll be addressing to all your doubts, and be very attentive in this first class of organic chemistry, because this is what will be required a lot. Next we'll see this one, third one. CH3 whole 2 CH CH3 CH2 whole 3 NO2. Okay, so first see, this 2 CH3 is attached, so it is like this, CH3, then this carbon is CH. Okay, then we have CH3 here, right? 2 CH3 to this 1 carbon, then you have again CH, and then 1 CH3 is there, then you have CH2 3 times, CH2 CH2 CH2, then you have NO2, right? So in the one chain, how many carbon we have? 1 2 3 4 5 and 6, right? So I will have 1 2 3 4 5 and 6. Let's draw it. Okay, so on this last carbon you have NO2 group, so just write down that one. Okay, then on this 1 2 3 and 4th carbon you have CH3 group, 1 2 3 4. Okay, then on the 5th carbon also you have CH3 group. Okay, so you don't have to write. Okay, since we are doing just the bond line formula, and just put lines. That's enough to show that here is one CH3 group and here is one CH3 group. So how can I draw it? It can be like this, right? Just converting this one, and then here one branch and here one branch. Okay, okay, 4th one also I want to do for you, because here there is CN, which is little bit different. Okay, so let's do that as well. Okay, so now if I do the 4th one, okay, you can see CN whole 2 CH CH2 CO Cl. So you have CH, you have CN whole 2, right? So here one CN and here one CN. Then you have CH2. Then you have COCl. So now see, if I draw CCl, there already 2 bonds are there, so oxygen will have 2 bonds. Okay, this is the structure. Now how many carbon I have? 1 2 3 and 3 carbon are in one chain. This is CN, this is CN. So 3 carbon I will draw, right? 1 2 and 3. Okay, now in this carbon there is CO and Cl, so I will join one O group and then Cl. The second carbon is completely CH2, the third carbon is having CN and CN. Okay, that is the bond line structure for the 4th one. Clear? Okay, now if this much is clear to you, let's move forward towards bond and hybridization. Okay, so first of all, if you know what is hybridization, hybridization is very basic thing, that the atomic orbitals, okay, atomic orbitals will undergo a mixing, okay, undergo a mixing before forming bonds. Now for example, carbon, and let me give a small example of, see, let's go little bit detail here. Suppose I have CH4. What is the hybrid carbon electronic configuration? 1s2, 2s2, 2p2, right? If I draw like this, so this is just to understand what is hybridization. Now carbon has to form 4 bonds, right? So it need 4 unpaired electrons. So 4 unpaired electrons, to get that 1 electron is excited here. So I will get 2s2, sorry, 2s, 1 second, just a minute, yeah. So this becomes now 2s1 and 2p3. What happens here? Excited state, right? This 1 electron goes there. Okay, now what will happen? These all orbitals, so 1s and 3p orbitals will undergo mixing. Okay, now these 4 orbitals have undergone mixing to give you 4 new hybrid orbitals. Okay, so this is also sp3 here, you have this is also sp3, and this is also sp3, and this is also sp3. Now there is no s orbital, no p orbital, each orbital is sp3 now. Okay, and generally hybrid orbitals we denote like this. Okay, clear? So now if I go back to our lecture, so what all, so we'll talk about hybridization. Before that, types of bond. So we have 2 types of bond. One is your sigma, okay, and another is called as pi. Denoted sigma like this, pi is denoted like this. Okay, now sigma bond means what? Sigma bond is always formed by hybrid orbitals. Okay, that is why I told you what is hybrid orbitals. So sigma bond is formed by hybrid orbitals, and pi bond is formed by unhybrid orbitals. Okay, unhybrid orbitals. Okay, now if there is one bond between carbon, okay, if there is only one bond between carbon, then this bond has to be a sigma bond. If there are 2 bonds between carbon and carbon, the first bond definitely is sigma, but the second bond is pi. Okay, next if I have 3 bonds, okay, the first bond is sigma, the second 2 is pi bonds. Okay, so always the first bond between 2 carbon is a sigma bond, whereas the second 2 bonds between the carbon, second 1 bond, or you can also have a 2 bond, these are your pi bonds. Okay, now if I talk about hybridization, now how to calculate, I told you what is the meaning of hybridization, but how to calculate the hybridization? So number of sigma bonds plus lone pair, that is your hybridization. If the number of sigma bonds plus lone pair is 4, then the hybridization will be sp3. If the number of sigma bonds plus lone pair is 3, then it is sp2 hybridization. And if there is number of sigma bonds plus lone pair is 2, then the hybridization is sp. Okay, and here also let me tell you about the geometry. Yes, so for sp3 hybridization, the geometry is tetrahedral. You should remember this one. Okay, then for sp2 hybridization, it is trigonal planar. Okay, then for sp hybridization, it is linear. Clear? Understood? So if this addition comes out to be 4, it is sp3, 3 sp2 and 2 sp. Okay, now you don't have to remember that 4 means sp3, just add here 1s and 3p, total is 4, so that is why here 4. 1s and 2p, total is 3, so here is 3. 1s and 1p, so it is total 2 here, right? Okay, now let's do some question. Here for each of the carbon, you have to tell what is its hybridization, how many sigma bonds are there and how many pi bonds are there. Okay, so let's start with the first question. Okay, so if you see the first question here, this carbon has 1, 2, 3 and 4. 4 sigma bonds are there. So this carbon, what is the hybridization? sp3. Now let's talk about this this carbon. Here also 1, 2, 3 and 4. 4 sigma bonds are there. So this carbon is also sp3. Now if I talk about this particular carbon, you see this is sigma and this is sigma, right? You have 1, 2 and 3. 3 sigma bonds are there. If 3 sigma bonds are there, then this is pi bond, right? It is a double bond, means it is a pi bond. So 3 sigma bonds and no lone pair. So this carbon is sp2 hybridization. And if I see this carbon, here also I have 3 sigma bonds. This is sigma and this is sigma. So it is also sp2 hybridization. So how many sigma bonds in total I have? Total sigma bonds 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And how many pi bonds you have? 1 pi bond. Clear? Sigma and pi, how to count? Is it clear? Next, moving to this question. Here also you have to calculate the hybridization. For this particular carbon, you see this is 1 sigma bond, this is 1 sigma bond. Only 2 sigma bonds are there. So this one is which hybridization? sp. Here also this carbon, this is 1 sigma, this is 1 sigma. Only 2 sigma. So this is also sp. Now this carbon has 1, 2 and 3. 3 sigma bonds are there. So this is sp2. This carbon 1, 2 and 3. So this is also sp2. And this carbon is sp3 because it has 4 sigma bonds, right? Moving forward here, this carbon 4 sigma bonds, so it is sp3. This carbon 1, 2, 3, this is pi bond. Okay, not only between carbon and carbon, between carbon and oxygen also, first bond is sigma, the second bond is pi. So I will only count the sigma bonds for hybridization. So 1, 2 and 3. 3 sigma bonds, so it is sp2. Here if I see 1, 2, 3, 4, 4 sigma bonds, so it is sp3. Here if I see 1, 2, 3, so it is sp2. Here I have 1, 2 and 3, so it is sp2. Here you can see 1, 2, 3, 4, so it is sp3. Here I can see 1, 2, 3, 4, so it is also sp3. Here I have here I have 1 and 2, right? So this is also sp. Right? Okay. Now moving to this one, you can see this carbon 4 sigma bonds, so it is sp3. This carbon 4 sigma bonds, sp3. This carbon 1, 2, 3 sigma bonds, sp2. This carbon 3 sigma bond, sp2. This carbon 3 sigma bond, sp2. This carbon 2 sigma bond, sp. This carbon 2 sigma bond, sp. This carbon 4 sigma bonds, sp3. Clear? Okay. Next we have degree of hydrogen. Okay, degree of carbon and hydrogen. This is very important when you read about what you'll say when you talk about carbocation and stability and all. So we need to understand the degree of carbon. Now what is this degree of carbon? So for degree of carbon we have primary degree, secondary degree, tertiary degree and quaternary degree. Now see, if one carbon, okay, if a carbon is attached to only one other carbon, okay, for example if I write like this, see this carbon is attached to only one carbon, so and this carbon will be called as a primary carbon. Okay. Now if I talk about secondary carbon, suppose I have like this. Now see, this second carbon is attached to 2 carbons, right? So if one carbon is attached to 2 carbons, then it is called as a secondary carbon. Okay, this carbon is attached to only one carbon, so this is primary. This carbon is attached to only one carbon, so this is also primary. Okay, next if I have primary and then I have tertiary. So if I have one carbon attached to 3 carbons, okay, so now see this particular carbon is attached to 3 carbons, so this carbon is your tertiary carbon. This carbon is attached to one carbon, directly primary. This is also primary and this is also primary carbon. Now if I talk about quaternary, quaternary means one carbon is attached to 4 other carbons. Okay, so if one carbon is attached to 4 different carbons, then this is called as your quaternary carbon. Clear? Primary, secondary, tertiary and quaternary. Now if I talk about hydrogens, okay, so in hydrogens we don't have quaternary, we only have primary, secondary and tertiary. The same thing, if you have understood primary carbon, now see, suppose this one is there, I'll take the same example. Okay, this carbon is primary because it is attached to one carbon, so all the hydrogens that is attached to this particular carbon, these hydrogens are also primary hydrogens. Now this carbon is also primary because it is attached to one carbon, so this carbon is primary and the hydrogen attached to the primary carbon are also primary hydrogen. Now let's take one more example. Secondary, CH3, CH2, CH3. Now see, this carbon is secondary because it is attached to 2 carbons, so this hydrogen is also secondary, this hydrogen is also secondary. This carbon is primary, the first one, because it is attached to only one carbon, so these 3 hydrogens are what? Primary. And this carbon is also primary because it is attached to this particular carbon, only one carbon, so these 3 hydrogens are also primary. Okay, now let's go to the third one, tertiary. So if you have like this structure like this, now see, this carbon is tertiary. Why? Because it is attached to 3 carbons. This is tertiary carbon, so the hydrogen attached to this tertiary carbon is also tertiary. Okay, I hope this is very simple, you can use it. And now see, this primary, secondary and tertiary can only be applied to sp3 hybridized carbon. sp3 hybridized carbon means carbon which has 4 sigma bonds. The carbon which has 4 sigma bonds, there only we can talk about primary, secondary, tertiary, quaternary. Okay, so now let's do some question. So we will be doing those same examples that we have discussed before. So I have to do what? I have to first find out yes, which carbon. So this is not, this is sp2, this is sp2, so these we cannot talk about their degree here. Here I can talk about the degree. Now see, this carbon is attached to only one carbon, so definitely this is primary. This carbon is attached to 2 carbons, right? This carbon and this carbon, so this is a secondary. Okay, that's it. Now you can go to here, this is not sp2, this is not sp2, this is not sp3, 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 this is sp3. Now this carbon is attached to a single carbon, so this is a primary group. Next we have here, this is not sp3, this is not sp3, this is sp3, right? 4 sigma bonds. Now you see, this carbon is attached to how many carbons? 1, 2 and 3. 3 carbons, so it is tertiary. Right, this carbon is not sp3, this carbon is also having 4 sigma bonds, but how many carbons it is attached? 1 and 2, so this carbon is secondary. Okay, now coming here, you see this carbon, it is attached to 1 carbon this side, 1 carbon this side and 1 carbon this side, 3 carbons, so this is your tertiary carbon. Now this is not sp3, no need to check, this carbon is sp3, but it is attached to only 1 carbon, so this is primary. Okay, so I have one tertiary, one secondary, another tertiary and one primary carbon here. Now moving forward to the next question, you see this, we'll talk about the first carbon here. Okay, so it is not attached to any carbon, right? It is not attached to any carbon, so we can give it a 0 degree, or this is also we can say not eligible for primary, secondary or tertiary. Now if I talk about this carbon, this carbon is attached to only 1 carbon, right? So this is what? This is a primary carbon. Now if I talk about this carbon and this carbon, there is no sp2, no sp3, they are also not sp3, this is also not sp3, no here. Yes, this carbon is attached to 1 carbon, so it is a primary carbon, right? Fine. Now let's see the next example. Here there is a very special example of methyl like CH3O, right? So here you see this is an sp3 hybridized carbon, but it is not attached to any other carbon. So this primary, secondary and tertiary quaternary does not apply to this particular carbon. Now coming here, it is attached to only 1 carbon, so it is definitely primary. Here it is not sp3, not sp3, not sp3, not sp3, not sp3. Here also it is attached to only 1 carbon, so this is also primary. Okay, I hope this is clear. Okay, now next moving forward to the second topic of our lecture, that is nomenclature. Okay, very important thing, nomenclature. So this is a basic outline of a IUPAC nomenclature where you write the name of the compounds. Okay, so we have a lot of names, right? But there's a scientific name that is given to each and every compound following a basic rule, and that rule I will discuss here, but the basic outline of a nomenclature of an organic compound follows this thing. So first you should always think about this word root. Okay, what is word root we will discuss. So there is a word root, there is a primary suffix. So word root, how it is determined? Word root is determined by the number of carbon in the main chain or in the longest chain. Okay, how many number of carbons are there? Based on that we have this word root. Okay, first thing. Then the primary suffix comes based on the carbon-carbon bond. Okay, so if the carbon-carbon bond is a single bond, then the suffix used is AN. If it is a double bond, then we use EN. If it is a triple bond, we use YN. Okay, this E will not come. AN, EN, YN based on what is the carbon-carbon bond. Next, the secondary suffix comes based on the functional group. Whatever is the functional group present in the compound, that will determine the secondary suffix. Now coming to the prefix part, the primary prefix is any cyclo. If there is a cyclic compound, okay, then we have to use this cyclo word if there is a cyclic compound. If not, directly we can use the secondary prefix. Secondary prefix is either about a side chain, okay, or a secondary functional group. Okay, so what is this side chain or secondary functional group? We will see in the examples. Now let's move forward here. So as I told you, first thing is word root, right? So in word root, if you have one carbon, we have to use the word root mit, 2 carbon ith, 3 carbon prop, 4th carbon but, 5th carbon pent, 6 carbon hex, 7 carbon hept, 8 carbon oct, 9 carbon non, 10 carbon dec. Okay, this is the word root that we will be using. Now the primary suffix part, okay, the carbon bond. So if there is a single bond ANE, double bond ENE, triple bond YNE. Okay, next secondary suffix, that is your primary functional group. So if it is a carboxylic acid, you have to use the word oic acid, means the suffix should be like this. For ester group it is OAT, for nitrile group it is nitrile, for aldehyde group it is AL, for ketone group ONE, for alcohol group for alcohol group it is OL, okay, OL, and for amine it is amine. So these are the suffix to be used for the primary functional groups to be used as a suffix. Next will come out to be the secondary prefix. So if you remember, primary prefix is the cyclic one, if there is a cyclic compound involved there. And here if I see, if the substituent is CH3 group, the prefix used is methyl, C2H5 2 carbon, so ethyl, OCH3 1 carbon, methoxy, OC2H5 2 carbon, ethoxy, F fluoro, Cl chloro, Br bromo, I iodo, NO2 nitro, NO nitroso, NH2 amino. Okay, so these are your suffix and prefix that has to be used for a name. Now I'll tell you the rules, it will be more clear. Okay, we'll discuss the rules. So first of all, step 1, what you have to do, identify the longest carbon chain. Okay, you have to identify the longest carbon chain. This parent chain, whatever you identify here, the longest carbon chain, that will be determining your word root. Okay. Next, you have to number the carbon atoms. This is very tricky and the most important part. Okay. Now you have to number the carbon atoms in such a way that if there is any functional group or if there is any substituents, that should get the lowest number. Okay, when we'll do example, it will be more clear. So prioritize the functional groups and substituents when numbering. Prioritize means you should number it in such a way that if there is any substituent or if there is any functional group, those groups should get the least number. Okay, next we have name the substituents. So now we will start writing the name. So you have to name all the substituents in alphabetical order. So whatever substituents are there, we have to write them with their position. With position means it is attached to second carbon, third carbon, fourth carbon. Okay, so with their position you have to write in the alphabetical order. Then locate the functional groups. Why do we need functional groups? Because these are going to be your suffix part, right? So name the name according to the priority order. I'll be telling you the priority order as well, and then combine all the things. So root, so I got the prefix part, I got the word root, and I got the suffix part here. So combine root name, suffix and prefix to get the IUPAC nomenclature. This may not be clear to you, but don't worry, we will discuss examples for you. Okay, so order you can see the first is your carboxylic acid, priority order of the functional group. This is very important. After that we have sulfonylic acid, sulfonic acid, then you have acid anhydride, you have esters, acid chlorides, then you have amides, then we have nitriles, then aldehydes, ketones, alcohols, and then amides. Okay, aldehydes, ketones, and then amides. So this order you should remember. Okay, fine. Now let's move forward. So now let's solve some question here. So you have this compound. Okay, first you have to identify the longest carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 carbons longest chain is there. Now whether we should number from this side or this side. Ma'am, functional group is given more priority. Here functional group is present. So we will number it in such a way that the carbon containing the functional group will get the least number. So I have to number it from this side. So I will have 1, 2, 3, 4, 5, 6, 7 and 8. Okay, now I have got the functional group, substituents and word root as well. So let's assemble them. So 8 is there, right? So what is the word root for 8? Oct. Okay, now is there any carbon-carbon double bond? No, it's only single bond. So oct, AN is the primary suffix. Then we have to mention the functional group. For OH the suffix used is OL, but it is on which carbon? Third carbon. So I will write 3OL, and then we also have to write the prefix, that is your substituent, that is methyl group. Which carbon? 6. So 6 methyl octane 3OL. Okay, now moving to the next one. Here I have two functional groups. You can see one is acid functional group. Okay, one is acid functional group and the other one is a ketone functional group, and we know that acids are given more priority than ketone. So the priority order I have shown you, acids are the one which is having the highest priority. So I have to number it from this way. Okay, 1, 2, 3, 4, 5 and 6. So if I number it from this way, so fifth carbon is the functional group. When ketone group is used as a substituent, the term used is oxo. Okay, so what is the word root here? Definitely hex. Okay, no carbon-carbon double bond, so AN. Okay, primary suffix is done. Secondary suffix is due to the functional group, so oic acid. And before that I have to put the prefix. So here it is oxo at what position? 5 position. So 5 oxo hexanoic acid. Okay, so this is some examples. We will practice more examples here, some more here and there we'll do. Then we will go to the next topic. Okay, thank you. So now let's continue the IUPAC nomenclature for some more compounds. Okay, so now some basic things you should be knowing when you have double bond and triple bond. Okay, so when we have double bond and triple bond, the ending name should always be with YNE. Okay, and you have to number the chain in such a way that the double bond and triple bond should get less number. Okay, now let's take one example here. Okay, these two examples are very, very important, so please understand carefully. Let's talk about the first one. Now if I number it from this side, 1, 2, 3, 4 and 5. So the double bonds are coming on which carbon? 1, 3, and 5, right? Now if I number it from the other side, okay, let's take green numbering 1, 2, 3, 4 and 5. Okay, so now on which carbon I am getting the numbering? See, first carbon, then on third carbon, and then on the, sorry, not third carbon, sorry, one second, first carbon, one second, just let me number it properly. Okay, so I have 1, yeah, I have 1, 2, 3, 4, 5, 6. Now if I number from this side, then I am getting on first carbon, third carbon and on the fifth carbon. Now you see from both the side 135 and 135, then which is the correct one? If you are getting same number from both the sides, then you should give more priority to double bond. Okay, more priority to the double bond. So I will say this numbering. So if I am going on this side, I am getting double bond on first and third, and if I go from this side, I am getting on third and fifth. So that is not correct. The double bond should get lower priority number, so I have to number it in this way. Now how many carbons are there? There are 6 carbon, and double bond number on which carbon the double bond is present, that can be written before the name starts. So I have on 1 and 3 third position, right? So I can write 1 and 3, 1, 3, hex, di for 2, then En you have to write. Di represents 2 double bond, En represents for Ene. Okay, then you have to write the carbon on which the triple bond is present, 5, right? 5 Yne. I hope this is clear. You have to number, if the numbers are coming same, then you should give less number to the double bond. Now see this one, this is very important. Now see, if I number it on this particular carbon, okay, let me take black color here. Okay, now see, if I number from this side, I am getting 1, 2, 3, 4 and 5. Okay, so my bonds are present on first carbon and on third carbon, 1 and 3. Now if I number it from this side, 1, 2, 3, 4 and 5. So the bonds are present on second and fourth carbon. So second and fourth are more than 1 and 3. Our first priority should be to number it in such a way that the bonds should get the least number. So this is the correct numbering. But here you see, if I number in this way, triple bond is getting more priority than double bond, or triple bond is getting less number than double bond. That is okay. Okay, here since it was getting same number on both the sides, we should give less number to the double bond. But here if I give less number to the double bond, then I have to number it from this side, and overall the numbering or overall the priority will become less. So this is the correct way of numbering. So I will have what name here? I have 5 carbon. On third carbon I have this one double bond. So I will write 3 pent En. Okay. Then on first carbon 1 Yne. Okay, clear? Now let's see this one. Here also double bond is there here. So double bond should get the first priority before the substituent. So 1, 2, 3, 4, 5 and 6. Okay, so on fifth carbon I have substituent. So I will write here first substituent name 5,5 dimethyl, 5,5 dimethyl. Okay, then you have hex 1 Ene. Okay, 5,5 dimethyl hex 1 Ene. Okay, next let's do this type of question. Here you have one, this is what, this side if nothing is there means it is H. We learnt this in writing bond formula and all, right? So aldehyde group will have more priority. That is why this one numbering will start from this carbon 1, 2, 3 and 4. Okay, so what will be the name here? But. I can write 3 but En. Okay, that represents the double bond is present on the third carbon, and I have 3 methyl also, right? So let me just change this one. 1 second. Yes, 1, 2, 3 and 4. So I can write like this: 3 methyl, this is for this one, 3 methyl but 3 En Okay, you can write this 3 here also. Okay, that is also correct. But 3En Al. Now this Al represents the aldehyde group. You don't have to mention 1 because aldehyde are terminal groups. They are always present at the end only. Okay, next if I do this question, it's very similar to the first one. 1, 2, 3 and 4. Here you have to name the substituent name. So I just have simply 3-methyl but ANAL. Right, AN and EN, you are getting the difference. Here we have double bond, so EN. Here there is single bond, so AL. Okay, next 2 more questions. Let's try here. This is acid group. Acid group will get the first priority. 1, 2, 3, 4. Right, so this is very simple, and we have here I can write 3-but En. You can write this 3 here also. Okay, but 3En or 3-but En, oic acid. When I am not mentioning when it is on the first carbon, you can skip writing the position of the carboxylic group. Now coming to the next question here, you have to number it in such a way that this carbon gets the least number. Why? Because it has the functional group. So I will number 1, 2, 3, 4 and 5. On the third group I have a substituent here. So I can write this one like 3-methyl, right? Then you have pentane 2OL. Okay, why I am writing 2 here? To represent this OH group. Clear? Okay, so students, this is all about nomenclature. Okay, you can practice as many questions as you can. So you can just open your NCERT Organic Part 2 book and go to the exercise section. You will get a lot of practice on nomenclature. I want you all people to try those nomenclature. Now let's move to the third important topic of organic chemistry, that is isomerism. Okay, if you are a little bit tired, if you are a little bit what I'll say, burnout, take 5 minutes break here, because we are going to start something very, very important, isomerism. So what is isomerism? Isomerism means they have same molecular formula, but at least one different physical or chemical property should be there. Okay, such type of compounds are called as isomers. Okay, now what are the type of isomers? We have basically 2 types of isomers. One is your structural isomerism, another is your stereoisomerism. In structural isomerism, we have these 4 types. One is your chain isomerism, functional isomerism, positional isomerism and metamerism. And in stereoisomerism, you have geometrical isomerism and optical isomerism. Okay, so please have a look on this flow chart. We will be discussing each and every isomerism in detail. Okay, so let's go back to first chain isomerism. Chain isomerism means we have different carbons chain, different carbon chain. Okay, for example, you have a formula C4H10. Okay, now I can have a structure like this here, CH3, CH2, CH2 and CH3. Now in this chain there are 4 carbons, right? I can write another formula for the same thing, CH3, CH3, CH3. Now you see in this particular there are 3 carbons in one chain, and here we have 4 carbons in one chain. So when you have different chain, different carbons of different chain, that is called as chain isomerism. Okay, now let's talk about positional isomerism. Okay, so I'll take another formula here. Let me take C5H12. Okay, so or let me take a functional group, that will be more clear. Just a minute. Let me just take the C4H9Cl. Okay, so here this one is C. Don't get confused. C4H9Cl. Now you see here, I'll put one formula like this, CH3, CH2, CH2, CH2Cl. Here one carbon is having Cl on the first position. I can have another isomer like this, CH3, CH2, CHCl and CH3. This is the second carbon, right? The Cl group is present on the second carbon. So you see the difference in the position of the functional group. Such type of isomers are called as positional isomers. Okay. Next, moving to the third one, functional isomerism. Now let me take an example of okay, so suppose I have C2H6O. This compound is given to you. Now I can have one isomer like this, CH3CH2OH, right? You can see this is what? This is an alcohol functional group, right? I can also have an isomer like this, CH3OCH3. Okay, this is what? Ether. So when you have the same formula, but you can write two different type of functional groups out of that, that is called as functional isomerism. Now let's talk about metamerism. In metamerism, you can generally find in ketones and you can find in ethers. Okay, generally. Now suppose, see, I have a formula like this, CH3, or I'll just write down. Okay, so suppose I have, let me think of an example. Yeah, I have an ether like this. Sorry, not ether, a ketone like this. Okay, so you see on the two sides of the carbon, I have two carbons here and I have two carbons here. What I can do another time possibility is I can write it like this. Right, you see on this, on the side of these group, I have one carbon here and I have three carbons here. Or better, you can also replace a more better example, if or more it is mostly found in ether. So let me convert it into a ether group. Okay, let this be a ether group. So now you see, besides this oxygen there are two carbon, but beside this oxygen there is 1 and 3 carbon. Such type of isomers are called as your metamers. Clear? So I hope all the types of structural isomerism is clear to you. Now we'll talk about stereoisomerism. In stereoisomerism, what is the difference between structural and stereoisomerism? The first difference is, see, in structural isomerism, the bonding is different. You can see everywhere. See, for example, here the bond is, there is an OH bond is present, here there is no OH bond is present. Here there is, the bonding only is different, right? The different types of new in this, the bonding pattern here and the bonding pattern here will be completely different. In structural isomers, the bonding pattern of carbon, hydrogen and other elements is different. But in stereoisomerism, the bonding is exactly the same, but still they have different arrangement in the space. So that is why they are called as stereoisomers. So what are stereoisomers? They have same bonding, okay, but different arrangement in space. Okay, clear this one? So geometrical isomerism, here you should know geometrical isomerism is of two types. One is cis and trans. Okay, another type is of E and Z. Okay, let me give you a very simple example here. Suppose I have a compound like this, and this is generally found in alkenes. Okay, generally found in alkenes. So if I have CH3, C double bond, CH3, H and H. This is one arrangement of this molecule. Another arrangement is CH3, okay. Now you see here the CH3 groups are on the same side, right? This type of arrangement where the same groups are present, this is called as cis arrangement. And we have CH3 groups on the opposite side, then this is called as trans arrangement, right? Cis group, CH3 on the same group, trans group, CH3 on the opposite side. So whenever we have same groups on the same side, we call it cis. When we have same group on the opposite side, we call it trans. Clear? Now every time we cannot have the same group. Now there is some example here. Let me take a compound like this. OH, CH3, this side I have Cl, this side I have H. Okay, just let me draw a margin here. Okay, now see this example. Here what happens? Here you see there is no group. How will you compare which is same, which is different? So for that we give numbering. Okay, so now this side, whosoever atomic mass is more, like carbon is attached to oxygen, carbon is attached to carbon. Oxygen atomic mass is 16, carbon atomic mass is 12. So this side will have more priority. So this will have more priority. This one will get number 1. This one will get number 2. Okay. Now similarly here if you see chlorine has more mass. So this one will get number 1 and this one will get number 2. Now 1 and 1 are on the same side. 2 and 2 are on the same side. So if they are on the same side, then we call it as Z isomer. Okay. Next, if I have this one, let me take the same compound like this, and here I have H and here I have Cl. So here definitely this is 2, this is 1, right? And here this is 1 and this is 2. Now 1 are on the opposite side, 2 are on the opposite side, Z, so this is called as E. Okay, E isomer, Z isomer. Clear? Now you can see here that the bonding is exactly same. What is this bonding for this carbon? It is bonded to one CH3 group and one H group in the cis isomer. In the trans isomer also this carbon is bonded to one H group and one CH3 group. But their arrangement in the space is different, but bonding is exactly same. This type of isomers are called as stereoisomers. Okay, so this is first type where we have geometrical isomers cis and trans, E and Z, and it is generally found in alkenes. Now we will talk about something called as optical isomers. Okay, so optical isomers are what? These are pair of compounds, okay, which can rotate the plane polarized light. Okay, now a question may be there, what is plane polarized light? So don't have to worry that much. Just think that this is a type of light which has only, electric and magnetic fields are present in the waves. So these are the types of lights where we have only one type of field. Okay, so any compound which is able to rotate this plane polarized light, means you have, suppose your sample here. Okay, you are giving this plane polarized light. Okay, your sample is present here, that organic compound is present here. If this plane polarized light will have only one field, right? So after passing through this sample, if this field is rotated, then this compound is called as optically active. This compound will be called as optically active. Okay, if it is able to rotate this plane polarized light. Now if this compound is able to rotate the plane polarized light, then it is called as optically active. I hope this is clear. Now suppose this compound is rotating it in clockwise direction. There will be another pair of compound, or there will be another compound similar to this which will rotate it in the anti-clockwise direction. Those two pairs are called as your enantiomers, and those two will be having non-superimposable mirror images. I know this is not clear, let me repeat it. Suppose here is a compound, let's see B. This compound is B. Okay, it is rotating the plane polarized light in this direction. There will be another compound which will be the mirror image of B. Okay, this compound. Now this compound will rotate this light in anti-clockwise direction. Now this B and B, these two are called as what? These are called as enantiomers. Okay, I hope it is clear. Or let me explain one more time. I'll try to explain this one. Okay, just a minute. Yeah. Okay, so we are talking about something called as optical isomers. So first thing you should be knowing is optical isomers are those compounds which can rotate the plane polarized light. Suppose we have a sample here. Okay, one organic compound B is present. Okay, this compound is like this. You are giving here plain polarized light, means which has only one field. It has field in only one direction. Now after passing through the solution, what happens? It rotates the plane polarized light. Okay. After passing through the solution, it rotates the plane polarized light. Now if you see, this has rotated in which direction? It has rotation in clockwise direction. There will be another compound. What is that another compound? The mirror image of this compound, this one. Okay, this one will rotate it in anti-clockwise direction. Now these two compounds will be called as enantiomers. I hope this is clear, and that is what is your optical isomers. So what are optical isomers? Let us write down this one. So we are generally, when I talk about optical isomers, we talk about enantiomers. Okay, what are these enantiomers? These are non-superimposable mirror images, okay, that can rotate plane polarized light. Okay, this is clear? Fine. Now we will move towards general organic chemistry, something very, very important. Now general organic chemistry deals with the basics of organic chemistry. If you understand this general organic chemistry, you will be able to understand the complex reaction mechanisms, which product will form, which one will not form, you will be able to predict. Okay, and this is the most important thing that you must know before entering your class 12, because in class 12 there are so many reactions, and if you go and memorize each and every reaction, you will do mistake. But if you know the logic behind every reaction, why this product is formed, why this is not formed, if you understand the logic properly, then you can do the questions very, very in a very convenient way. Okay, otherwise you have to mug up and then you will mess it up. So what all things we are going to see in general organic chemistry? We will see first electronic displacement, electrophile and nucleophile, carbocation, and then type of reactions. Okay, so first let's talk about the topic electronic displacement. Before that, we'll understand a reaction generally, how does it takes place. We have a substrate, then we have an attacking reagent, and then once these two reacts, either we get a transition state or an intermediate, and finally the product is formed. Now in this substrate, what all things we will learn? In this substrate we will learn the electronic effects. Okay, what are the electronic effects we have here? We have inductive effect. Okay, we have here mesomeric effect. You might be thinking what ma'am is telling, but just wait, you will understand. Hyperconjugation. Okay, these all things we see for a substrate, mesomeric or resonance. Okay, now the attacking reagent, what does we see? We see in an attacking reagent whether it is a nucleophile or an electrophile. Okay, next intermediate, what do we see? We see the stability of carbocation here, stability of carbocation or carboanion or free radical. Okay, these three are intermediates, but generally we study about carbocation. That is what will be mostly required in your class 12. Finally, products will form. Okay, so first we will see about these three things. Okay, inductive effect, mesomeric effect, and hyperconjugation. So students, I am guessing that the lecture has become very long, but still if you have continued watching till here, please don't go back now, don't turn off the video. Here we are going to discuss many important things here. Hardly it will take another 40 to 50, I think 40 or 30 minutes. So please continue the video. Okay, fine. let's move towards the electronic effects that we are talking about. So inductive effect, resonance or mesomeric effect, then we have hyperconjugation effect. Okay, so let's start with inductive effect. So what is inductive effect? It is the shifting of the electrons from low electronegative element to high electronegative element. Okay, let me give you an example. Suppose I have HCl. Okay, this bond will have 2 electrons. Every bond has 2 electrons. Okay, now chlorine is more electronegative. So what will happen? Because it is more electronegative, these electrons will slightly shift towards chlorine. Okay, now when this shifting slightly takes place, this chlorine gets a slightly negative charge and hydrogen gets a slightly positive charge, delta negative and delta positive. Okay, so here what I can say is, now the chlorine which is pulling the electrons, okay, which is giving the electrons, we call it as minus I effect. Okay, and the hydrogen which is giving the electrons, okay, which is pushing the electrons, that is called as your plus I effect. Okay, minus I effect means the one which takes the electron. Plus I effect means the one which pushes the electrons. This one is pulling, this one is pushing. Okay, so plus I effect means the one which donates the electrons. Okay, it is donating the electron. Here this one is which one? Or you can write down accepting the electrons. Okay, so now we will see the factors on which this inductive effect depends. The first factor is distance, very important. So the inductive effect decreases with distance. Okay, please write down this one. I am not writing the statement. Inductive effect decreases with distance. For example, if I have like this, okay, now chlorine will pull electron here. This is delta minus, this is delta plus. Now these 2 carbon which is far away, they will have delta plus 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 plus, means here the positive charge will be more, here less, here less. Okay, so the inductive effect will keep on, here it is more, and as we move towards the end it keeps on decreasing. Okay, this is what the inductive effect on the distance. Next, degree of carbon. So here you should know tertiary, secondary and primary. Tertiary will have more inductive effect, that is like this. Okay, tertiary will have more inductive effect. Then we will have secondary, and finally we will have primary. Okay, next talking about hybridization. So sp will have more inductive effect, then sp2 carbon and then sp3 carbon. Okay, so these 3 factors you have to remember. Now let's talk about some groups which can show minus I effect. So for example, all halogens. Okay, then you have OH group. Okay, then you have NH2 group. Okay, then you have OR group, you have NR group. Okay, and then you can write even CF3 group, CN group, NO2 group. Okay, these all groups will withdraw electrons and show minus I effect. Okay, they will withdraw electrons, means they will pull the electrons towards itself. Withdraw electrons towards itself. Okay, clear? Now talking about plus I effect. What is plus I effect here? Plus I effect means the one here alkyl groups. Alkyl groups shows plus I effect. Okay, so here suppose we have an example, CH3 group, CH2CH3, and we have CH2CH2CH3. Then where the inductive effect will be more? Inductive effect will be more here, then here, then here. So more carbon, more inductive effect. Okay, Clear this one? Okay, next we will move to resonance and mesomeric effect. Okay, so what is resonance here? The shifting of pi electrons in a conjugated system is only between the carbons is called as a resonance. Okay, so for example, you can see here 3 boys are there. Okay, so these ball, if they are passing the ball, these balls are your electrons. Just imagine. So if the electrons can move from one person to another, then we call it resonance. Okay, similarly, if these pi electrons, which electrons will move? This is very important. Pi electrons will move, right? So these pi electrons, okay, if there are 3 carbons are there, they're moving. Why this? It can move here because there is a vacancy here, lone plus charge is there. This is called carbocation, right? So if the electrons can move from here to here, they exchange electrons, and this is called as resonance. Now first let us see what is mesomeric effect then. If in resonance there were 3 boys, right? But in here, if we have any other species other than carbon, here you can see carbon, carbon, and then CN group is there, right? So these type of resonance where any other element is involved, okay, that type of elements are called as that type of resonance is called as mesomeric effect. So here this should be a functional group. Okay, this F group represents functional group. So here what I can conclude, that every mesomeric effect is a resonance. Okay, but every resonance is not a mesomeric effect. Okay, resonance can only be when you are saying between carbon to carbon, but if any functional group is involved, then we call it a mesomeric effect. Okay, now we will see what is this conjugated system. So I told you for resonance, conjugated system is mandatory, and there are 4 types of conjugated system that we can have. The first one is when you have double bond, single bond, okay, and here you have a negative charge. Okay, double bond, single bond, and then a negative charge. When I represent 2 electrons, it is a negative charge. Okay, double bond, single bond, positive charge. Here also resonance is possible. If you have double bond, single bond, and a free radical, okay, here also resonance is possible. And next you have double bond, single bond, again double bond. That type of resonance is also possible. So you have pi, sigma, lone pair. Here lone pair, negative charge, anything will work. Pi, sigma, positive charge. Pi, sigma, free radical. Pi, sigma, pi. Okay, if these type of systems are present, then we call it as a resonance is possible. Okay. Now we will see some types of resonance, like we had seen here types of inductive effect, right? Plus R, plus I, minus I. Similarly, we have plus M, plus mesomeric and minus mesomeric. Now see, if this one is there, okay, here what will happen, this OH will donate electrons to the ring. Okay, it will donate because it has lone pair of electrons, it will donate the pair of electrons. If it is donating, any species which is having lone pair, it will donate. Okay, so if it is donating, then it is called as what? This is called as plus M effect. Donates pair of electrons. Okay, next, if it withdraws electron, you can see this oxygen, you have double bond, single bond, double bond. So this oxygen is more electronegative, it takes the electron towards itself, then these bond shifts here. So if the group takes the, here this group is giving the electron, here this group is taking the electron. So if it takes the electron or withdraws the pair of electrons, then it is called as minus M effect. Okay, clear? Now we will do more questions. It will clear how to find out which is plus M, which is minus M. Okay. Now there is one more basic comparison. You see this particular structure. NH, if you remember, I told you it is an electronegative element. So it will show what? It will pull the electron towards itself. So it will show minus I effect. NH group will show minus I effect. At the same time, it is a lone pair. So it will also donate. It will show plus M effect also, minus I effect also. Then which is more dominant? Out of plus M and minus I, always mesomeric effect is more dominant, or mesomeric effect is more effective. Clear? Now if I talk about, this is for all the groups except we have halogens. In case of halogens, if you see, they have lone pair. They can donate, right? So see, halogens can also donate electrons. they will show plus M, and because they are electronegative, they will pull electrons, they will also show minus I. But in case of halogens, minus I is more dominant than plus M. Okay. Next, we will talk about each of these examples and see whether it is plus M or minus whatever. So now you see here, oxygen is there. It is having lone pair of electrons, so it will donate electrons to this one, right? So this has plus M effect. Okay, but it is an electronegative element, so this is plus M effect. This is plus M effect, but it is having also electronegative element, so it will pull the electrons towards itself, so it is minus I effect. But which is dominant here? Plus M is dominant. So OH shows plus M effect. Now CN, if you see, CN what it will do? It will pull the electrons. Okay, CN, if you just draw the structure, I'll just expand this side. CN is like this. Okay, so here there is a double bond. So what it will do? It will pull the electrons towards itself. So it has minus M, and also CN is electronegative. It is also minus I. Both will take the electrons. Next, here in benzene there is no group, so here we don't have anything. NH2, it will donate electrons, so it is plus M, and since it is electronegative, it will have minus I effect. Okay. So overall, what will be the objective? It will be plus M. Then here F, what will happen? It will donate the electrons plus M, and it will withdraw the electrons minus I. So I know for halogens, inductive effect will be more effective, so it will have minus I effect. Next we have CH3 group. CH3 group, you should remember, it has only plus I effect. It will donate to the ring. NO2 group, if I draw the structure of NO2, it is like this. Okay, and here if you see the double bond, so this will, what it will do? It will withdraw electrons from the ring, and nitrogen is electronegative, so minus I also. Okay, both minus and minus I. Here oxygen will donate electrons to the ring because it has lone pair, so plus M. Since it is electronegative, it will withdraw minus I. So overall it will have plus M because mesomeric effect is more dominant. NH, if you see, this will donate, so it is plus M. This is electronegative, it will withdraw minus I, so the final effect will be plus M. Okay. Next, here we have this group. Now here what will happen? Oxygen is more electronegative, so it will pull the electron towards itself. This one will also pull the electron itself. It will have minus M and also minus I. Okay. I hope this is clear. Fine. Next, we will move to something third effect, that is hyperconjugation. Now hyperconjugation is the sigma electrons typically from CH or CC bond are delocalized into an adjacent empty or partially filled p orbital or a pi system. Now we will see example and understand. See, so first, before that, let us see what is alpha carbon and alpha hydrogen. The first carbon, suppose this is a double bond, right? This first carbon is called as the alpha carbon, and the hydrogen attached to it is called as alpha hydrogen. So there are 3 alpha hydrogen. Here if you see, this is the functional group, right? So this carbon and this carbon are alpha carbon. Okay, and total how many I have? 6 alpha hydrogen. Here if I see, this is positive charge, so this is alpha carbon and you have 3 alpha hydrogen. Okay, clear? Fine. Next if we talk about hyperconjugation. Okay, so first of all, see, we will understand now hyperconjugation. See, this structure I can represent like this. Okay, so what happens now? This sigma bond electron can shift from here to here. Okay, so what will happen? This electron will come here. I can draw it like this. See, I'll draw it like this. First one, if this happens, I'll get C, then I will have H, then you have C, H, right? One electron has come here, and this H means both the electrons will come here and H will present as H plus. This bond has broken, right? That is one possibility. That is a possibility that this bond has also shifted here. That is also a possibility there. If that happens, what will happen? You will get C, this one is there, okay, and you have H plus. right? This bond has broken and this one will give you H plus. There's another probability that this bond can also break, right? This bond can break and give the H plus here. If that happens, what will be the structure? You have C, H, H, and here the bond is there, that is broken. Then you have C, double bond, you have H, H, and here you have electrons. This bond is broken. So now you can see that this particular carbocation is stabilized due to these alpha hydrogens. So what we can conclude? More alpha hydrogen I have in the next slide. So okay, and more alpha hydrogen, more stability. Okay, so where is this hyperconjugation concept applied? It is applied in three cases. One is in the case of alkenes. Okay, in the case of, first of all, in the case of carbocation, in case of alkenes, and then in the case of free radical. Okay, in these three places we can apply hyperconjugation. So let's see whether hyperconjugation is present in these compounds or not. Here do we find any carbocation? No. Alkene? No. Free radical? No. Okay. Next, here I can find a carbocation. Yes, we can apply hyperconjugation here. Here can I find any carbocation? No. Alkene? No. Free radical? No. Here, yes, alkene is present, free radical is present, right? So while talking about the stability of this carbocation, stability of this alkene, stability of this free radical, we have to use the concept of hyperconjugation. And to remember this, you can use a mnemonic CAF, CAF, carbocation, alkene, free radical. Okay, clear? Now let's see the importance of hyperconjugation. So if more number of alpha hydrogen will be present, more hyperconjugation will be there, more stability will be there. Okay, let's see with example. Suppose this, we want to talk about the stability of the carbocation. If I talk about this carbon, this is alpha carbon, this is alpha carbon, this is also alpha carbon. So we have 3 alpha carbon, so that means we have 9 alpha hydrogen here, right? 9 alpha hydrogen is present. Then if I have this one, here I have 1 alpha carbon and 1 alpha carbon, so total I have 6 alpha hydrogen. Here I have 3 alpha hydrogen and here there is 0 alpha hydrogen, right? So if there is, this is not 3 alpha hydrogen. What is alpha hydrogen? Carbon. So what is alpha carbon? Carbon attached to the functional group, first carbon attached to the functional group or any other carbocation. So the first carbon here, these all are first carbon, these all are first carbon, this is 1 carbon, there is no alpha carbon, so no alpha hydrogen. So what is the stability? This is the order of stability. More alpha hydrogen, more hyperconjugation, more stability. Clear? Let's see next topic, that is electrophile and nucleophiles. Okay, so electrophile and nucleophile, we will talk about their definitions and examples. Nucleophile is something which is rich in electron species, which is rich in electrons. Okay, so these are the species that donate a pair of electrons to form a covalent bond. So they can be either, they can be either neutral or negative species. And what are electrophile? These are the species which is electron deficient. They are generally positively charged. For example, here if you see, we have electronegative species like Cn minus, F minus, OH minus, OR minus, NH3 neutral species, H2O. These all are nucleophiles. Now if I talk about electrophiles, so if I have a carbon oxygen bond, right, this carbon delta plus, because this is oxygen is more electronegative, so this carbon is electrophile. If I have CX bond, this is delta negative, this is delta positive, so this is electrophile in nature, right? Next I have C plus, any carbocation is there, that is also electrophile. Okay, where there is deficiency in electrons. Okay, now we will talk about carbocation. Okay, so their stability and definition. Carbocation stability is very, very important. Majority of the things lies around this stability of carbocation, and we will do a lot of questions from this topic now. Okay, so first of all, stability, how do, okay, there's, let me briefly define what is a carbocation. So carbocation is a carbon species with a positively charged, okay, and generally this carbocation is sp2 hybridized. Okay, so that much you should know about a carbocation. Now let's talk about the stability. So the stability is affected by three factors. The first one is resonance. If there is a resonance stabilized carbocation, it will be highly stable, then hyperconjugation, then inductive effect. This is the order you should follow. So we will do example and that will be clear. Now see, for example, this question, I will see there is no resonance here, because we know for resonance what we have seen, what is the mandatory condition for resonance? We need to have conjugation. And how we have conjugation? Double bond, single bond, positive charge, double bond, single bond, negative charge, double bond, single bond, lone pair, double bond, single bond, double bond. Okay, these type of systems should be there, but here we don't find any such system, so there is no resonance here. So let's see hyperconjugation now. If I see hyperconjugation, here I have alpha carbons, 3 alpha carbons, so I will have 9 alpha hydrogen. Okay, here I have 6 alpha hydrogen, here I have 3 alpha hydrogen, and here I have 0 alpha hydrogen. So what is the order of stability of this carbocation? This is the order, right? Now let's talk about next example. I will see this particular question. Now see this carbon, okay, so this carbon, alpha carbon is this one, and this carbon is the alpha carbon. Here I have 2 hydrogens and here I have 1 hydrogen, right? So total this compound has 3 alpha hydrogen. Okay, if I talk about this one, this carbon, so this is the alpha carbon, this is the alpha carbon, and this is the alpha carbon. So here I have CH3, so 3 hydrogen, 2 hydrogen, 2 hydrogen. So I have here 7 alpha hydrogen. Now if I see here this carbon, this is H here, right? This carbon, this is H here, and this is having 1 alpha hydrogen. Okay, so here I have A, here suppose B, and here suppose C. So more number of alpha hydrogens means more number of stability. So the order of stability will be BAC, right? Now we will talk about resonance. Here you can see resonance, right, in the second example. See, double bond, single bond, positive charge, double bond, single bond, positive charge. So here I can find 2 resonances are there, right? Here I have single resonance, here no resonance. So if this is A, this is B, and this is C, then the order of stability will be A, B, and C, right? Let's see this one. Okay, here you can see there is resonance, right? Double bond, single bond, positive charge. Just first let me number it. Okay, now if I see this one, I will see what? Hyperconjugation. So here I have 2 hydrogens and here I have 3 hydrogens. So 3 plus 2, this compound is having 5 alpha hydrogen. This is CH3, this is CH3. This compound is having 6 alpha hydrogen. 6 alpha hydrogen. So more number of, so first of all we will see resonance. This compound is having resonance, so this is more stable. Now B and C is not having resonance, so the second factor we'll consider is hyperconjugation. According to hyperconjugation, 6 hydrogen here, 5 hydrogen here, this will be more stable. So A, C and B, right? Now let's do this next one. Here you see resonance is there. Here let me see, do we have resonance or not? See, double bond, single bond, positive bond, double bond, single bond, positive charge. So here resonance is there. Here double bond, single bond, single bond. Here there is no resonance. Double bond, single bond, single bond, single bond. Here also no resonance. So we will see hyperconjugation in these 2 structures. So let this be A, this be B, this be C. Now here if you see, this is positive charge. Here I have CH3 and this is CH2. Right? So 3 plus 2 we have 5 alpha hydrogen here. And if you see this one, here you have only this one compound CH2, 2 alpha hydrogen. 5 alpha hydrogen, 2 alpha hydrogen, and here it is resonance. Then what will be the order? You see A is the order because of resonance, then we have B, then we have C. Okay. Next we will have one exception here, okay, for resonance. You see this is benzyl carbocation, double bond, single bond, positive charge, right? This type of carbocation is called as benzylic carbocation. Here resonance is there, so that should be more stable, but resonance stabilized carbocation is also less stable than tertiary carbocation. Why? Because you can see we can have 9 alpha hydrogens here. So if this particular example is there, then do remember that tertiary carbocations are more stable, okay? And how do you find that? This is experimentally observed, experimentally found. Okay, clear? So this is the thing that you should remember. Tertiary carbocations are always more stable than benzylic carbocation, even though here we have resonance. Okay, I hope this exception, please put a red box here and write down this point. Fine. Now we will go to the next topic, that is types of reactions. This is the last topic for this video, and after this, this whole bridge course is the organic chemistry bridge course is going to end. So now we are going to study about the last part of this lecture, that is types of organic reactions. Okay, there are various types of reactions, but 3 major reactions are there, that is your substitution reaction, addition reaction and elimination reaction. Okay, so we will be understanding each of them with some example, and especially this addition reaction and elimination reaction, we have certain rules that we have to remember. So if you are taking notes, please be alert and make proper notes here, because this is very, very important. So moving towards now to substitution reaction. So what is substitution reaction? A group or atom of a substrate. Now in the starting I told you what is a substrate, the reactant, right? A group or atom of a substrate is replaced or substituted by another group of atom is of the reagent. Okay, let me give an example. So for example, I have this one. Okay, I have CH4. Okay, now if I am reacting this one with chlorine in presence of H nu. Okay, H nu means in the presence of light energy. So what product I will get? Do you know? We will get CH3Cl. So what you exactly observe? The hydrogen present here is replaced with a chlorine. Okay, so this part, this is called as a substitution reaction, where one atom of the reagent is substituting another atom of the substrate. Okay, so these type of reactions are called as substitution reaction. Another example you can have, for example, I have the same, I'll take CH3Cl, and if you treat it with OH minus, right, this is a nucleophile. So what will happen? This OH minus will replace this chlorine and you will get CH3OH, right? You can see this chlorine is replaced with this OH group. Okay, so this is the basic example of substitution reaction. Now let's move to the next reaction, that is addition reaction. So in addition reaction, what happens? A reaction in which 2 molecules combine to give you a single product is called as an addition reaction. Like normally we have studied about combination reaction, when 2 elements combine to give you one product, that is combination reaction. Similarly, when 2 reactants react to give you a single product, that is called as addition reaction. But one special thing you should know about addition reaction is it generally takes place with an alkene or a carbonyl group. Carbonyl group means either an aldehyde or ketone. Aldehyde or ketone. There can be other groups also where the addition reactions happens, but these are the 2 things which you will be studying mostly in your class 12. Okay, so let us take one basic example. Suppose I have C double bond, so alkene I am taking CH2. Okay, now suppose you are adding this one with Br2CCl4. So this is just a solvent, bromine is the reagent. So what will be the product here? Here the product will be, one second, yes. So I will have HH, and here I will have bromine. Okay, clear? So you are seeing this bromine is getting added to this double bond. So this one will give you a product. Two products, two reactants have mixed to give you one particular product. Now here something we should also know about Markovnikov's rule and anti-Markovnikov's rule. Now for this you have to understand two important things. First is this rule. Okay, this rule is applicable to unsymmetrical alkenes. Okay, first of all it is applicable to unsymmetrical alkenes. Okay, and where we have to use this rule? While the addition of HX, HOH, okay, generally when we are adding HX and HOH we have to use this rule. Now first I will tell you what is unsymmetrical alkenes. Now see, suppose I have this alkene CH3, CH, double bond, CH, CH3. Now what you have to see? You see this double bond, right? In the side of these double bond, the same groups are present, right? Or I can say that this alkene can be divided into two equal parts, right? This is one part, this is one part. This is your symmetrical alkene. Whereas if I have an example like this, CH3, CH, double bond, CH2. Here you see, this alkene, can we divide it into two equal parts? No. So this alkene is an example of symmetrical alkene, okay, and this example is of unsymmetrical alkene, right? So whenever we are adding what, HX or HOH to an unsymmetrical alkene, we need this Markovnikov and anti-Markovnikov rule. So let me repeat, when we will need this rule? We will need this rule when we are adding HX or HOH, that is water, to unsymmetrical alkene. We will require Markovnikov's and anti-Markovnikov's rule. Okay, so I will erase this one. I hope you have taken the note of this one. If not, please pause it, take the notes, and then we will go to this rule. Okay, so I'll erase, just I will add two things here. It is used for unsymmetrical alkenes and in the addition of HX, HOH. Okay. Now what is Markovnikov's rule? Markovnikov's rule says that negative part goes to carbon having less hydrogen. Okay. And anti-Markovnikov is just the opposite of this one. Okay. So let's see one example. Suppose I'll take an unsymmetrical alkene CH3 double CH double bond CH2. Okay. Now suppose for this one I am adding HBr. Okay. Now which is the negative part of this reagent? You know H plus and Br minus, right? Br is more electronegative. So bromine will pull the electron towards itself. By which effect? By minus I effect. We have studied inductive effect. So by minus I effect it will pull the electrons towards itself. So bromine will have a negative charge, a slightly negative charge. H will have a slightly positive charge. So I can say that this is the negative part. Now negative part will goes to the carbon having less number of hydrogen. So you have to first check this double bond. Now this is one carbon in the double bond, this is one carbon in the double bond. Let me use a different color. Yeah. So this is a carbon in double bond, this is a carbon in double bond. Now this carbon is having one hydrogen, this carbon is having two hydrogen. Right? So negative part will go to the carbon having less number of hydrogen. So what will be the product here? CH3. See, this negative part will go to the carbon having less number of hydrogen. So I will add here bromine and this H was already present. Then this bond will break. We are adding, right? So one bond will break and two new bonds will form. So I will have CH2 and one H is added here. I hope this is clear. Next, we will see anti-Markovnikov's rule. In this what happens? Just the opposite. Negative part goes to carbon with more number of hydrogen. Okay, and here this a rule is applicable to only one example. So that should be HBr in presence of peroxide. Okay, HBr in presence of peroxide if this reagent is given. Okay, only and only if this reagent is given. So please note down, very important, if only this reagent is given, then you have to follow anti-Markovnikov's rule. Okay, so here we will do the same question now. Yes, so I have this one, CH3 CH double bond CH2, and I added HBr with peroxide. So what will happen? The Br, the negative part, goes to the carbon with more number of hydrogen. Here there are 2 hydrogen, here there is 1 hydrogen. So the negative part will go to the carbon having more number of hydrogen. So what will be the product here? CH3 CH, here H will be added, and here CH2 Br. Right? Getting this one? So HBr peroxide if present, if HCl peroxide is given, then also it is not there. Only and only HBr peroxide if it is given, then we will have this product. Now let's do a few questions here. Okay, let's just practice certain questions. If you have like this, CH3 CH2 CH double bond CH2. Okay, so here I am adding HCl peroxide, you are adding HBr, you are adding Br2 CCl4, okay, and then you are adding H2O in presence of acidic medium. So these are the different additions we have given. Now let us try to find their product. Okay, so first of all, HCl is added. Which rule will be followed? There is no peroxide, so Markovnikov's rule will follow, and according to Markovnikov's rule, what will happen? The negative part will go to the carbon having less number of hydrogen. So chlorine, here 1 hydrogen, here 2 hydrogen. So negative part will go to the carbon having less number of hydrogen. So what will be the product here? CH3 CH2 CH, and here you have added Cl and then CH3. I hope you are getting this one. Negative part is added to the carbon having less number of hydrogen. Next we have HCl and peroxide. So with HCl, peroxide has no effect. Here also you will follow Markovnikov's rule. Okay, so again the same product I will get. So CH3 CH2 CHCl CH3. Next we have HBr with peroxide. So here what will happen? If we have HBr and peroxide, we will follow anti-Markovnikov's rule. What does anti-Markovnikov's rule say? The negative part will go to the carbon having more number of hydrogen. More number of hydrogen. Here I have 1 hydrogen, here I have 2 hydrogen. So bromine will go and attach to the carbon having more number of hydrogen. So bromine will attack here. So what will be the product formed? CH3 CH2 CH H CH2Br. Right? H and Br are attacked like this. Then Br2 CCl4. Here what happens? Both the groups will, double bond will break, and we will have here just like this, bromine and bromine. Okay, we will have 2 bromine groups attached on the double bond. Next, water. Water is like this. You have H plus is positive and OH minus is negative. Right? So negative part will go to the carbon having less number of hydrogen. So what I will get here? CH3 CH2, and then we have CH OH, and then I have CH3. Okay, negative part will go to the carbon having less number of hydrogen. Clear? So I hope with this example you have practiced certain questions on addition reaction. Okay, now we will go to next thing, that is your elimination reaction we have discussed. Oops, sorry. Okay, We have discussed addition reaction, Markovnikov and anti-Markovnikov's rule. Now let's move to elimination reaction. Okay, now elimination reaction, what does it tell? A reaction in which one molecule splits to give you two product is called as an elimination reaction. Basically, you should remember the product is mostly an alkene here. For example, suppose I have just a minute. Okay, yeah. So for example, if I have like this CH2 means CH3 and CH2OH. Okay, and here what happens, you take here concentrated H2SO4. Now concentrated H2SO4 is a dehydrating agent. It will always remove water. So what will happen, this H and OH will be removed. So what will be the product here, CH2 double bond CH2 plus water, right? So you can see one product breaks to give you two product, and majorly in elimination reaction the product formed is your alkene. Okay, and this is for removal of water, you can use concentrated H2SO4. If I have something like this CH2Cl like this. Okay, so if I want to remove this HX, you have to use the reagent alcoholic KOH. Okay, you will be studying this in detail. I am giving you some hint. If you use alcoholic KOH, this HCl will be removed and we will get a double bond here. Okay, plus HCl is the product, right? Now here also one rule you should follow. Here this is a symmetrical alkene, so removing is very easy. Now let me give you an example. Suppose I have, we'll talk about the Setzeff rule, but let me give you an example. Suppose I have like the CH3, just a minute. Okay. CH3, CH2, I have CHCl and CH3. Okay, and then you are giving here alcoholic KOH. Now what is the role of this alcoholic KOH? Alcoholic KOH, if you remember this reagent from now onwards, its work is to remove what? HX. Okay, to remove HX. Now here I can find HX, here also I can find HX, means this HCl can also be removed, right? Or this HCl can also be removed, right? So let this one, if this HCl is removed, the product A will form. If this one will remove, product B will form. So what will be my product A here? Product A is, I am removing this HCl. So double bond will come here. So I will get CH3, CH2. Then here this, I think you can see here, this H and Cl will remove, a double bond will come here. So I will get CH double bond CH2. This is product A. Now what is product B here? In product B, what will happen? This HCl and H and Cl will remove and this one will be double bond. So I will have CH3, CH double bond CH and CH3, right? These are the two products formed. Now what we have to see, that whether this is the major product or this is the major product. Here the term or the knowledge of hyperconjugation will be required. Now what we have studied, remember, more is the alpha hydrogen, more alpha hydrogen, more stability of alkene, more stability of alkene. Okay. Now what you have to see, you have to take this double bond as a functional group. Okay, this double bond as a group. Now to this double bond, how many alpha hydrogens are there, you have to count. See, the alpha, this is your alpha carbon, right? This is alpha carbon, this is alpha carbon, and two hydrogens are attached here, so I have two alpha hydrogens, right? Now here if I compare, to this, right? So how many alpha hydrogens I have? See, this is also alpha carbon, this is also alpha carbon, so I have total 6 alpha hydrogens. So I have, for this product A, I have 2 alpha hydrogen, and for product B, I have 6 alpha hydrogen. So which will be more stable? More alpha hydrogen, more is the stability of the alkene. So I can say that product B will be more stable, right? So if this is more stable, then product B will be the major product. Okay, this will be the major product and this one will not form, or this will be the minor product. Okay, so if question is asked what is the product, you have to write this one. Okay, you don't have to write this one. This will be the major product, so I will eliminate option number A now. Okay, so this will not be the product. Getting? I hope this is clear. Now then, what is Setzeff rule? So Setzeff rule tells that during elimination reaction, okay, during elimination reaction, more substituted alkene is formed. Okay, during elimination reaction, more substituted alkene is formed. I hope you are getting this one. So that is what you have to do. More alpha hydrogen, more stability. So like this, we'll do one more question. It will be more clear. Okay, let's do a question like this. I have CH3, Cl. Okay, then I have CH2, CH3. Okay, and I am having here alcoholic KOH. Okay, so what are the hydrogens I have available? First, let me show you that. Okay, so you have a hydrogen here and you have a hydrogen here. Okay, so there's a possibility that this HCl will be removed, or there's a possibility that this HCl will be removed. So let this be product A, this be product B. Let's try writing both the products. So what will be my product A? So I have CH3, okay, then I have CH3, then I have, if I am removing this one HCl, okay, so here I will have a double bond, then I have CH and then CH3. And let me see if I have product B, where I am removing this one, this double bond. Okay, so I will get CH2 double bond C, CH3, then I have CH2, CH3. Okay, now let's see the alpha carbon. Okay, so if I consider this double bond, okay, this is my functional group. So this is alpha carbon, this is alpha carbon. So total 3 and 2, I have 5 alpha hydrogens. Now here if I consider, this is the alpha carbon, this is the alpha carbon and this is the alpha carbon. So I have how many? 3, 3, 3, 9 alpha hydrogens. So definitely this is the major product, right? So this product will not form. A will be the major product, right? So like this you can identify the major product, right? So this will be the product, one and only product formed here. Both major and minor will form, but always you have to write the major product in the answer. Okay, so students, I think with this we are done with the lecture. We have completed all the important things that is required for organic chemistry or to enter to class 12 organic chemistry. We have discussed nomenclature, isomerism, general organic chemistry. Then we have also discussed about different types of carbon and all. And this will be definitely will create a foundation, a base for your class 12 chemistry. So I know the video is a bit lengthy, but yes, this is your one video that you can watch and have a proper base for your organic chemistry. I hope this video was helpful. If you have any doubt, please put down in the comment section. I will definitely answer to it, and stay tuned for the next lectures and all the very best.